You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Würth Elektronik technical specialists. We'll be shining a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast. Impedance and capacitance spectra, or scattering parameters, are very common representations of frequency-dependent electrical properties of the capacitor. The interpretation of all these spectra provides a very wide range of electromechanical, physical, and even technical information. Those need to be separated from the ever-present measurement artifacts as well as parasitic effects. Now, we know it's not always possible to provide all the data in the data sheets, so you as an engineer may have to utilize measured spectra to choose a suitable component for your circuit design. To provide the best possible database, we've implemented the online tool RedExpert, where spectra as well as other measurements are provided. In this podcast, we'll be recapping the properties of the spectra and also discuss how basic electrical characteristics can be inferred from it.
Hello, everyone. As already announced today, I would like to talk about impedance spectra of capacitor technologies and how to interpret them. My name, as already mentioned, is René Kalbitz. I'm working in the capacitor department for Würth Elektronik. Here, I'm responsible for the supercapacitors and capacitor-related research projects. There's a manifold of capacitor technologies. Each have their specific charge storage process. Just to give you some examples. Polymer electronic capacitors utilize the large polarizability of conductive polymers. The mechanism of electrical conductivity of conducting polymers is based on the transmission of so-called polarons. For supercapacitors, two charge storage mechanisms need to be considered: Faradaic charge storage as well as non-Faradaic. For electric double-layer capacitors, which is the most relevant group of supercapacitors, charges are stored at the interface in a so-called Helmholtz plane in a non-Faradaic process. Ceramic capacitors make use of a charge displacement within the unit cell of the lattice structure of the ceramic, which in some cases may even depend on the applied DC voltage. Here we see impedance and normalized capacitance spectra, which are typical for EDLCs, that is supercapacitor, electrolytic capacitors, as well as multi-layer ceramic capacitors, or MLCC. Without going too much into detail, due to the use technology and processes, each spectrum has its own characteristic and is located at different frequencies, as you can see. Especially the capacitance spectra looks quite different for each technology. For all measurements, it is required to have a model in order to interpret the measurement results. It is common practice to use equivalent circuits for the interpretation of capacitance spectra. Here you may see a few examples that can be used to interpret, for instance, supercapacitors, MLCCs, or ECAPs, and many more. The circuits model so-called bipolarization, polarizations at the interface, and so on. It is at this point no use to get too much into detail. I just wanted to show you these circuits to point out the complexity of capacitive charge storage if it comes to modeling. However, for electrical engineering, the data interpretation and the modeling can be much simplified. We are lucky. We mostly need one single model. With that single model, it is possible to retrieve the electrical parameters of practically all capacitors on the market. I mean, there are a few examples where you cannot use it, but most of the time you are well served with this single model. In the course of the talk, I will explain how to use the model for the interpretation of the spectra. We will have a look at spectra for high and low capacitive parts and discuss the issue of loss angle accuracy and the ESR measurement. You may use a simple capacitor sign in your circuit diagram. However, the actual circuit, as used, for instance, in LT-SPICE simulation, is the circuit just below. Let's have a closer look at the model. The model consists of an ideal capacitor CS, an ohmic equivalent series resistance named RESR. The ESR models all energy dissipative processes that restricts charge movement. In real life, it depends on temperature, frequency, and other parameters, but in most cases, the ohmic behavior is sufficiently good for the description of the spectra and to understand them. So this resistance here is responsible for the fact that our parts sometimes get warm. Also, the leakage current is modeled as an ohmic resistance, but with a much higher resistivity. It is called in this graph here R leak, which in most cases can be even neglected because it is high ohmic. Since all capacitors are connected by metal leads and current collectors, we also have to consider a small inductance, the equivalent series inductance called LESL. The ESL is, however, not a design parameter. It is due to metal leads, metal traces, and metal current collectors, and so on. And yeah, depending on the exact PCB layout, it may vary from application to application. The equivalent circuit is merely a representation that helps visually. One may discuss certain behavior qualitatively pretty good with this one already. More important, however, is the mathematical representation, since this one is ultimately used to extract values from measurements, or it is used for the simulations. Again, we do not need to discuss the formula at this point. I just want to show you that it is a function with a real and imaginary part that consists or that contains all the elements or parameters of the equivalent circuit which I have just discussed. So you will find all the values which are here are somehow also modeled here. The model can also be translated into a vector representation where the abscissa represents the real values and the ordinate represents the imaginary values. So the inductive and capacitive reactance relate to the ordinate and the resistance, like the ESR, to the abscissa. The vector representation is very useful to illustrate the relations between each component. Important for the accuracy of the measurement is the loss angle, for instance, denoted as delta here in the vector representation. And we will talk about this later in this talk. Here's an example. We see a fit of this model to a group of MLCC impedance spectra. It illustrates the influence of the capacitance variation on the position of the impedance curve. And I just wanted to give you an argument that you really trust me. Okay, if you can model this with this, it is a good model. As a matter of fact, the capacitor can act as a capacitor, as resistor, as inductor, or as a resonator. It all depends on the frequency. There are several characteristic frequencies that determine which parts or units of the circuit is active. At those characteristic frequencies, the spectra show specific features, as we will see later. Each characteristic frequency is related to the interaction of two components usually. For instance, at low frequency, the pure capacitance couples with a leakage resistance, forming the characteristic frequency of the CR leak unit, or denoted F leak. In the mid and high frequency range, the capacitance may couple either with the ESR or with the parasitic inductance, forming the FRC or FLC frequency. Also at high frequencies, the ESR can couple with a parasitic inductance, and that usually happens at the frequency I denote as FRL. Before we go to the measurements, let's have a closer look at the impedance spectra calculated by the model. The advantage of the theoretical graph is I can show the behavior of the entire spectra over a wide frequency range and discuss all features very nicely. Here I have calculated the spectra with values based on a film capacitor with a capacitance of 4.7 microfarads. It may serve as an example for low capacitive parts. How can we interpret the spectra and what data can be extracted? The most important feature in this graph is the minimum at the characteristic frequency of the LC unit. At this frequency, the spectrum has a sharp minimum. The position is determined by the capacitance and the parasitic inductance. The ESR measurement is most accurate around this region. The minimum value of the impedance is actually the ESR at this specific frequency. Towards higher frequency, we see an increase of impedance. In this region, the spectrum is dominated by the parasitic inductance. Thus, it acts as an inductor. Towards lower frequencies, the impedance increases as well. However, this part of the spectrum is dominated by the pure capacitance. At very low frequencies, usually well below 1 Hertz, the impedance curve shows a shoulder, which is situated at the characteristic frequency of the CR leak unit or F leak. At this point, the capacitor acts as high ohmic resistor. Thus, below this frequency, the leakage resistance can be simply read off, can be inferred from the graph. Maybe I should say could be inferred, since you may see it only for a very leaky capacitor, or if you would measure towards very low frequencies, which you cannot do with any equipment. You need a special impedance analyzer, but you can measure it nonetheless. The spectrum here is calculated such as to fit values from a 50 farad supercapacitor. It may serve as an example for high capacitive parts. Let's start with the most important frequency range between 1 Hertz and 1 megahertz. High capacitive parts show a bathtub-like shape and not a sharp minimum, as shown before. The bottom of the graph, however, is centered around the characteristic frequency of the LC unit. The entire bottom region is dominated by the ESR. So in this area, the ESR can be extracted with high accuracy or basically read off directly from the graph. The onset of the capacitive parts towards lower frequencies is at the characteristic frequency of the RC unit, FRC here. Below that frequency, the capacitor is dominated by the capacitive part and actually starts to act as an capacitor. Above the characteristic frequency of the RL unit, that is here, the capacitor starts to act as an inductor. The frequencies around here of 10 to minus 10 to 10 to minus 12 are incredibly low and nearly impossible to measure. Even with the right equipment, it would take ages. However, I wanted to have it just for the sake of completeness and for educational reasons, that you really see, okay, here we have this behavior, which I have shown before as well. So we can also see the influence of the leakage current in such cases. Also interesting for the device characterization are capacitance spectra, as shown here. The two depicted capacitance spectra are again for the 50 farad supercapacitor and the 4.7 microfarad film capacitor. The graphs are representatives again for high and low capacitive parts. The orange graph for the supercapacitor shows the shoulder at the characteristic frequency F RC. This is a typical behavior for large capacitors. All large capacitors, if you like, show this type of shoulder. The height of the shoulder gives the capacitance of the part. Above this frequency, the capacitance in the spectra goes towards 0. Hence, above that frequency, the capacitor cannot be fully charged anymore. The spectrum of the 4.7 microfarad capacitor looks quite different, as you can see. That is what typically capacitance spectra of low capacitive parts look like. At low frequencies, they show a clear capacitive behavior. The most striking feature, however, is the strong asymptotic behavior at the characteristic LC frequency. At this point, capacitance and parasitic inductance leads to a resonating behavior, and above the characteristic LC frequency, the capacitance again actually tends towards 0, meaning the capacitor cannot be charged anymore. So what is something you have to keep in mind, or you should keep in mind? No matter what the actual capacitor technology you consider, it's mainly its capacitance value that will determine the overall appearance of the spectrum. To demonstrate that, I have prepared an animation. I hope I can start this one. The only thing I change here is the capacitance. I go from high to low capacitance, and as you can see, the shoulder changes gradually from this shoulder to this spiky asymptotic behavior. And all I'm doing is changing the capacitance. So enough of the theoretical graphs and consideration. Let's have a look at the measured spectra of a 50 farad supercap. It may serve, again, as already mentioned, as an example for high capacitive parts. The impedance spectrum shows, as in the calculations before, a bathtub-like laser pointer. Here we have it, laser pointer. A bathtub-like progression, as can be seen on the top left graph here. This flat bottom region represents pretty much the ESR of the supercap. As you can see, the curve progression compares to the ESR plot below. That is the real part of the impedance. That is practically, in our model, the ESR. It has a slight increase towards lower frequencies. At high and low frequencies, the measurement accuracy of the loss angle prevents the correct separation of the capacitive reactance and the inductive reactance from the ESR. So that is around here and around here. This leads to a steep increase at high frequencies and a steep decrease at low frequencies at the corresponding characteristic frequencies. So the measurement of the ESR is most accurate between the characteristic frequency of the RC and the RL unit. The capacitance spectrum on the right-hand side shows the typical shoulder situated at the characteristic frequency of the RC unit at FRC. The height of the shoulder gives the capacitance of the device, in this case, around 50 farads. As a representation for a low capacitive part, I would like to show you the spectra of the 470 nanofarad film capacitor. The impedance spectra looks quite different from the one before. It has a sharp minimum at the characteristic frequency of the LC unit. As you know from the theoretical graphs, the minimum value is the ESR at the specific frequency. The ESR spectrum is largely influenced by the capacitive and the inductive reactance. It often does not reflect the actual ESR. I will come to this later and elaborate on that a bit more. Most trustworthy are the results around the characteristic frequency FRC. Towards higher and lower frequencies, it will be difficult for the impedance spectrometer to separate the imaginary from the real part. This usually leads to some kind of U-shaped spectrum with a local minimum around the characteristic LC frequency. The capacitance spectrum does not have a shoulder anymore. It will show this asymptotic behavior. This is actually a physically correct behavior, not just some artifact. The capacitance and the inductance constitute a resonating system leading to this Lorentz oscillation. For the developer, that means you stay away from that frequency. The capacitor can only be used below this frequency of the LC unit. In this region, the capacitance can then also be inferred from the spectrum. In this case, it's a bit higher than the rated one. It's 400 95 nanofarads. I have mentioned before that the ESR at the low and high frequency cannot be measured correctly. I want to discuss that on the example of low capacitive part. For frequencies well above the characteristic frequency, also below, the loss angle tends towards 0. As you can see here, you have a sharp rise of the loss angle at FLC, but if you go away further away from this frequency, it tends towards 0. However, the measurement device is only able to measure values above the accuracy limit. It cannot go to 0. Delta or tangents delta becomes a constant, therefore it cannot go below its accuracy. Thus, at some point, the real and imaginary part is not properly separated, and the ESR becomes practically proportional to the capacitive or inductive reactance. This is all due to the resolution limit. Let's exemplify the matter on spectra of an ECAP. The left graph shows the imaginary part, which is red, and the real part of the impedance. So red is the imaginary part of the impedance, and the blue is the real part. And what we also see is a fit of a model that describes the ESR. Usually, it has become established to use a law that is called Yoncha power law. Practically all ESR models are based on power laws, but I don't want to go too much into details at this point, but it is common practice to model ESR behavior with power law based models. Details are found in the literature and are given also on the slide. If you use such a model, then it is able to describe the region below, let's say, 1 kilohertz quite well. However, as the frequencies goes below, let's say, 100 hertz or so, the function strongly deviates from the measurement. This is around the frequency range when the loss angle gets close to its measurement accuracy, as you can see on this graph. At lower frequencies, the graph of the ESR runs then parallel to the graph of the imaginary part. I don't want to bother you with logarithmic law, but if you do the math, you will see that the proportionality will lead, the proportionality you have here will lead to a shift in the double logarithmic plot. I hope this will convince you that for low frequencies, the ESR spectrum does not actually show the ESR, but is influenced by the capacitive reactance. I may have pointed out some this detail here in more detail. This angle here, this is around the accuracy limit of the device which I'm using to actually measure this graph. So as a rule of thumb, you can keep in mind only use ESL values extracted around the minimum of the impedance or at the bottom of the impedance. The lower you get, the more likely it is that the ESR is overestimated. If you want to be really sure, you always have to look at the loss angle and have to search the manual for the accuracy limit of the device, and then you know exactly what values you can trust and where you start to overestimate your ESR. So the loss angle is essential if you want to make, the knowledge about the loss angle is essential if you want to make an accurate interpretation of the data. Does that mean that if the ESR increases, that it is always due to the increase of the imaginary part of the impedance? Well, hard to say, as long as the tangents delta cannot be measured accurately. If you don't have any information about that and you see these very strong increase, it is very likely that the ESR is largely overestimated, and you should start to be very suspicious about the values. Which brings me to the conclusion. What should you take home? For electrical engineering, only one model is required to describe all capacitors. It is a simplification, yes, but it is accurate enough. It describes all measured features. Also, it is the loss angle resolution that limits the accuracy of the ESR measurements. You should only trust values at the frequency range where the impedance shows a minimum. The lower the frequency, the less accurate the ESR measurements actually. The capacitance value, on the other hand, is best extracted at the low frequency and well below the characteristic RC or LC frequency.
We invite you to explore our capacitors and related components available at Würth Elektronik online. While you're there, for any questions, click on the icon to talk with our live chat team. You can also test drive the online tool Red Expert completely free of charge. Using this tool, you can download datasheets, make comparisons, and easily order free samples directly from the website. To view the materials discussed today and to replay the video, check out our YouTube page. You're listening to Würth Elektronik's What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists who are going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.